Welcome students to today's lecture. We are still discussing probability, and today we want to see the theorem that is used in solving probability of, or the chances or the likelihood of events happening or not happening. So today I would like us to discuss the inclusion or the exclusion principle. So the inclusion and exclusion principle, this box here clearly explain it well. We have a box, and think of it as if we have element A and element B. Element A is an individual and independent cycle. Then element B is also an individual and independent cycle. Then if you superimpose the cycle A on top of cycle B, then you will have the region of intersection. And the region of intersection is the point where some part of element B overlaps into some part of element A, this region here. So according to Venn diagram for two sets A and B suggests that to find the size of A union B, we add the size of A and the size of B. But then we have included the size of the intersection of A and B twice. So we have to take it off in terms of probability. And this is what is now called inclusion exclusion principle. So let's take an example in this proposition 1.7 that is saying the probability of the union A and B is given by the probability of A plus the probability of B minus the probability of A intersection B. Because we have included the intersection A and B twice, so we have to subtract it out. We now prove this from the axiom using the Venn diagram as a guide. We see that A union B is made up of three parts. Namely, if we take A1 is equal to A union B, A2 is equal to A minus B, and A3 is equal to B minus A. Indeed, we do have A union B being equal to A1 union A2 union A3, and we have seen that A1 is A intersection B, and A2 is A minus B, and A3 is B minus A. So we will all along proceed with this designation A1, A2, A3, keeping in mind their definitions. So since anything in A union B is in both these sets, or just the first or just the second, similarly we have A1 union A2 is equal to A, and A1 union A3 is equal to B. The set A1, A2, A3 are mutually disjoint. This means that we have three pairs of sets to check. Now A1 intersection A2 is an empty set, since all elements of A1 belong to B, but no element of A2 do. The argument for the other two pairs are similar. You should do them by yourself. So by example 3, we have that the probability of A is equal to the probability of A1 plus the probability of A2. And A1 we said is A intersection B, and A2 we said is A minus B. So then the probability of B is the same as probability of A1 plus probability of A3. I do think that now you remember that A3 is B minus A. So then the probability of A union B is equal to probability of A1 plus probability of A2 plus probability of A3. From this we obtain probability of A plus probability of B minus the probability of A intersection B is equal to the probability of A1 plus probability of A2 plus the probability of A1 plus probability of A3 minus the probability of A1. So this simplifies to probability of A1 plus probability of A2 plus probability of A3, which is the same as probability of A union B. As required, the inclusion exclusion principle extends to more than 2 events. So if we have 3 different events, this becomes more complicated. Okay, but we can try to prove this by taking the Venn diagram as a virtual box here, and the events A, B, and C as independent cycles. Then we try to superimpose them on top of the other. Then we can see we have three intersection cycles. So to calculate the probability of A union B union C, we first add a probability of A, probability of B, and probability of C. The parts in common have been counted twice. So we subtract probability of A intersection B, probability of A intersection C, and probability of B intersection C. But then we find that the outcomes lying in all 3 sets have been taken off completely, so must be put back. That is, we add the probability of the intersection A intersection B intersection C. So checking the proposition 1.8 for any 3 events, say event A, event B, event C, we have the probability of the union of A, union of B, union of C being equal to the probability of A plus probability of B plus probability of C minus the probability of A intersection B minus the probability of A intersection C minus the probability of B intersection C plus probability of A intersection B intersection C. That is how we solve the inclusion exclusion principle for 3 events. So other results about sets, we have let A, B be subsets of the sample space S. So the distributive laws state that the intersection of A and B together with the union of C is equal to the union of A and C and intersection of B and the union of C, and union of A, B and the intersection C is equal to the intersection of C and A union by the intersection of B and C. So De Morgan's law states that the union of AB complement is equal to A complement intersection B complement, and the intersection of A and B complement is equal to A complement union of B complement. So this marks the end of our today's lesson, students. Let's meet again in the next class.